Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we will continue our previous discussion on the concept of equilibrium. If you remember, last time we said that equilibrium condition is a compromised condition. It is not a condition where you do not have any disturbance, but it is a condition where you have all the disturbances, and actually in particular you have more than one sources of disturbances, and somehow it is a special condition at which all the sources of disturbances they are in such they arrange themselves in such a manner that the net effect of them will be cancelling and thereby giving you a net zero perturbation or net zero disturbance. Okay, this is a equilibrium condition. So, in the framework of classical mechanics, an equilibrium, which we also call a mechanical equilibrium, is defined by the condition where you have, if you have a particle of mass m and it is actually acted on by several force. I just draw for the sake of simplicity to understand. So, F1, F2, F3 like this, all are vectorially defined over here, F4, F5, F6. Then for example, we have a particle acted upon by 6 forces, and the condition of equilibrium will be summation over I is equal to 1 to 6 if I vectorial is a null vector. Okay. So, this is the concept of equilibrium. Now, we said that this is in general true and the force field need not be conservative in nature. We also showed two interesting examples. One, there is a balance between a conservative force field and a dissipative force field. So, the energy is not conserved, but the equilibrium is maintained. Also, we discussed another case where the energy is maintained, but equilibrium is not. That is a simple case where you have a single conservative force which is acting on a particle. So, the particle is accelerating, but the total mechanical energy is conserved. Okay. So, this type of thing is very usual in classical mechanics. One is true, the other is not. Okay. Now, whenever we are talking of conservative force fields and the concept of potentials, then we actually can introduce two supplementary concepts, which is a refinement of the concept of equilibrium. Then under that condition we have stable and unstable equilibria. Okay, equilibria is the plural form of equilibrium. So, and we already discussed that stable equilibrium means u, or the potential function has a local minimum, and unstable equilibrium means u has a local maximum. Let us say at some point x01 and at some point at x01 and at some point x02. Okay. So, we of course know at that point here of course that says du dx at x01 is 0 and d2u dx2 at x01 is greater than 0. Here du dx at x02 is 0.2 and d2u dx2 at x02 is less than 0. Okay. There is a third concept of neutral equilibrium. Neutral equilibrium is a condition which is a mixture of stable and unstable equilibrium, and I invite you to learn a little bit, okay, by yourselves. In some in a later lecture I will come to this concept, neutral equilibrium. So, once again, if you remember the last discussion, under a small perturbation actually every potential very close to the point of equilibrium, every potential can be thought of a simple harmonic type of potential like half k x square if k is greater than 0, and if the k is less than 0, then of course you can think of a inverted parabolic or inverted simple harmonic type of potential, which is actually the case of unstable equilibrium. Okay. So, what was the conclusion? The conclusion was that if a particle is slightly perturbed from its state of stable equilibrium, it will ideally perform a simple harmonic oscillation with respect to the point of equilibrium. And what about if we perturb some particle with respect to its point of unstable equilibrium? Either it kills that perturbation exponentially, or it increases its perturbation with respect to that point exponentially. In both cases, there is, in both cases for unstable equilibrium, the particle does not perform any type of simple harmonic oscillation. Okay. So, that is the basic difference between stable and unstable equilibria. Now, one point may come that what happens to this concept for more than one dimensions. So, of course, for more than one dimension, we of course know that we can have a potential function which is just a function of the space coordinates, and now we have actually, let us say it is a n dimensional problem and the space coordinates are x1, x2 up to xn. Then at equilibrium, so this is the potential, I should write like this, potential at equilibrium. Let us say this is at equilibrium, means this will be also a point in n dimensional space, let us say x01, x02 till x0n. At equilibrium, we have gradient of u to be equal to 0. Okay. That means that if you now remember this, it is del u del x0n for, I can say, yeah, I for all I running from 1 to, for all integral I of course running from 1 to small n, these will be equal to 0. Okay. So, that we have to make sure. Okay. So, this is a vector. So, this is 0 means this is a null vector, every component will be 0. Okay. Now, what about understanding the nature of the equilibrium, that whether the equilibrium is a stable one or an unstable one? Then we have to use the concept of Hessian. We have to construct a Hessian matrix, for the second derivatives of u. How it looks like? It simply looks like this. The second member will be del to u del x1 del x2, and then it will go till del to u del x1 del xn del to u del xn del x1, then finally you can easily see that will be simply del to u del xn 2. So, this is called the Hessian matrix, which is consisting of the second order derivatives of u, and then we say that u has local minimum if all the eigenvalues of H is real and positive, all of them. So, you have to calculate then the eigenvalues of this matrix, of this Hessian, and if you see that all the eigenvalues are real and positive, then it has a local minimum. So, that will correspond to a point of stable equilibrium in n dimensional space. N can be simply 2 or 3 and even higher dimension. For our case, just 2 or 3 is okay. U has local maximum if all the eigenvalues of H are, I mean I should say R here is, yeah, are real and negative, and this is the condition where we have unstable equilibrium in more than one dimensional space. In the assignment, I will give you a problem on that, and what you can enjoy and you can actually solve easily. Okay. Now, the point is there can be situations where some of the if I just write if some of the eigenvalues are positive and some are negative, then we talk of a saddle point. Saddle point is a very interesting situation where the particle cannot decide whether to follow or whether to behave according as the situation of a stable equilibrium or an unstable equilibrium. So, if you love horse riding, you see, I mean you always see that just for sitting there is something like this type of structures where you can, I can try to just draw that, and this type of structures are there. So, if you just, I mean it could be betterly drawn, but if you just see that with respect to this point, so there is a, I mean if you just follow this path, you can see this type of thing is there on the horse. Now, if you just follow this path, then you can see this middle point is the minimum, and so according as this region, this point may be regarded as a point of stable equilibrium. On the other hand, if you see this region which can be like this, thought like this, then with respect to this region, this point is the maximum, local maximum, and then it will actually if the point is, if the mass particle is at this point, it will not understand that whether it should follow the behavior, and if it is perturbed a little bit, whether it should follow the behavior of a stable equilibrium situation, that means to perform a oscillatory movement over here, or it has to exponentially go like this or exponentially kill its perturbative displacement. Okay. So, this is something which is very interesting, and my suggestion for you to be to search on this point over internet and let me know maybe in the forum, that what do you think if the particle from this point is perturbed slightly, in which way the particle would behave? Is it like it cannot be decided, or it will depend on some situations or whatever. Okay. Okay. So, at this point I can just tell you that this is the general concept of equilibrium, and this type of concepts can be actually, as I just discussed, that can be extended for every possible force, but only when you have conservative force fields, then you have potential, and then you can actually talk of a meaningful situation of unstable and stable equilibrium positions. Okay. Now, it is also true that in a motion, depending on the nature of the potential and the force, you can see that how many possible points of equilibrium situations that particle can have. There is no fixed rule for that. That means that one can actually, for example, if the potential, let us say, is like that. So, it has only one local maxima. So, this system can have some minimum at infinity. So, in finite displacements, in the framework of finite displacement, you cannot have for that particle any meaningful or any possible displacement where the particle is at stable equilibrium. On the other hand, if you have simply this, then it will only have a minimum over here. So, then this particle will never have a position of unstable equilibrium. Okay. In nature, most of the cases we encounter I mean potentials which are a little bit complicated than that, and let us say something like this. Okay. I mean I can just draw like this, sorry, yeah, like this, and here you can actually have like this, or you can have like this, okay, where you can have both points of stable and unstable equilibrium. Okay. Finally, before concluding, I once again encourage you to go back to the case of one dimensional motion and try to connect the concept of the saddle point and the concept of neutral equilibrium, which I deliberately avoided. Okay. And you let me know in one of the forum discussions. Okay. Thank you.